Okay. So we're going to get started. It's 4:30. We're starting with this problem about the limits of sequences. So last class we did limits of sequences. We're doing more limits today. There's going to be even more limits next week and 2 weeks from now. Maybe I'll wait a second until people quiet down. Okay, well, let me put the timer beeping back on. 2 seconds. Let's. Okay, so like I said, we're doing limits of sequences. We're starting this one, exercise 136. If you're just getting in, I'll give you a couple minutes to do it while I make some super quick announcements. One super quick announcement is that there is a lot of homework due on Monday. Why is there so much homework due on Monday? If you recall, after midterm 1, there was no homework because it was right after the midterm. That midterm, the homework was due this Monday. So if you haven't done it yet, you're just going to feel like a lot of homework on Monday. There's also the homework from the recorded lecture, the one that was canceled because of the last day before reading week. We canceled that in person, but I made a recorded lecture with homework to go with it. That's also due Monday. Plus, there's stuff from this week that is also due Monday. So lots of stuff due Monday. Don't leave it till the last second, or you're going to feel overwhelmed. The other thing, like I said last time, is I promise that every single homework set, I will take one problem like it and put it on the midterm exam. So I got rid of time limits on the homework. It's very easy. For example, you could go and use some kind of like special internet calculator to find the answers to the homework and get 100% on the homework without doing any work. If you want to do that, that's fine. I will get you back on midterm 2. So make sure you look at those problems and understand them. There's going to be similar ones on midterm 2. Last but not least, maybe even most important, some people were asking me, how do I access all the resources you were talking about last time? The Zoom online office hours, the in-person office hours, everything like that. It's all listed here under important links and resources on CourseLink. So if you haven't seen this page yet, I highly recommend you check it out. It has all these different things. Here's the recordings for the lectures. Here's the Zoom links. Here's the Math Learning Center. Extra videos. All this is here under important links and resources on CourseLink. Any other questions or comments about anything before we start? Okay, so we're going to start doing actual math then, and we're going to start with this limit, exercise 136 on page 310. It's the sequence minus 1 to the power n. And let's see what you guys said about the sequence minus 1 to the power n. What is a1? a1. 28 people said a1 was 1. Minus 1 to the power 1. That's what we're doing. 28 people said it's 1, but 1 is not right. 1 is not right. It's minus 1. 39 people said minus 1. So let's do this one maybe more slowly. We're looking at, oh, this is the wrong thing. We're at 4:30. Okay. Where are we? Here we are. Okay, so let's do this sequence slowly. So the sequence is an. The numbers n go 1, 2, 3, 4, as always. I'll wait a second for people to quiet down. Okay, so the numbers n go 1, 2, 3, 4. What is an doing? Well, when n equals 1, it's minus 1 to the power 1. Minus 1 to the power 1. And you should know that anything to the power 1 is just that number. So minus 1 to the power 1 is just minus 1, minus 1. Okay, next up is a2, minus 1 to the power 2. Did you guys figure out what minus 1 to the power 2 is? Lots of people said 2. It's not 2. It is not 2. It is 1 this time, 37 people. So like half the people got it right. 37 out of 76. Half the people got it right. 4, okay. All right, I'm not sure. So minus 1 squared, when you square negative 1 times negative 1, a negative times a negative is a positive. So you get positive 1, positive 1. Okay, what about a3? Minus 1 cubed. Again, like only half the people got it right. Some people thought it was 3. I don't know. I don't know why you think it's 3. Maybe you think the sequence is an equals n. It looks like there's a chunk of people not getting it right. An, when n is 3, minus 1 to the 3 is minus 1 again. Okay. There's lots of talking. Maybe there's some question, something I can clear up. Maybe it wasn't displaying correctly on Mathematize? Is there a question? Okay, if there's no question, I'm going to wait until people stop talking, and then I will continue. Okay, so what's the pattern? The pattern is you always multiply the previous number by -1. You multiply by -1. So you start with -1, you multiply by -1, you get +1, then you multiply by -1, you get -1. It goes -1, +1, -1, +1. The next term would be +1, and then the term after that is -1. It's this thing. And it's called the alternating sequence. It goes negative, positive, negative, positive. It's alternating between -1 and +1. All of that is warm-up. I thought that that would be very easy. The real question I want to get to is what is the limit? What is the limit? Let's see, how did people do on the limit? Which I thought finding the values would be okay, but let's look at what the limit. And it was multiple choice. So 0, 1, infinity. Okay, pretty split here evenly between all the options. Now that you guys know what the values are, so the largest category got like 20 answers out of 70. I'm going to let you guys revote. So let's try it one more time. I'll open it up again. Feel free to talk to your neighbors. What do you think the limit is? And we're going to revote. So repeat this one. And we'll revote. Okay, and I'll give you like a minute to try this. Okay. So yeah, the reason I'm waiting is people are still talking. Okay. So let's see what you guys said this time around. Reveal counts. All right, this time hopefully everybody got it. -1, 1, -1, amazing. Amazingly well done. Okay, but what is the limit? That's the question. What is the limit? And it's still somewhat split. So some people think the limit is 1. Did anybody think the limit was -1? Some people, but most people think it does not exist, but it's not infinity or minus infinity. That is the correct answer. So most people got it. The limit does not exist, but is not infinity or minus infinity. Let's go fill it in, our notes. So it does not exist, but is not infinity or minus infinity. And why is this true? So I would do it visually. I'm a visual type of person. I made a little pattern here where we can see it. Let's turn it on. I want this. Okay. And oh boy, everything is all messed up here. I think it's because I'm zoomed in a lot. Let's try zooming out. And let's try zooming out here. Okay. So here is a visual representation of the sequence. This is the kind of thing we saw last class. Let me try one of these. Okay. So here's the sequence shown visually. This is, I believe, what we called method 2 last class. So what does the sequence do? It goes -1, then it's 1. Then it's -1, then it's 1. Then it's -1, then it's 1. You can also ask Desmos to please connect the dots. Let's ask Desmos. Desmos, can you please connect the dots? And then you can see it going up and down and up and down. So it's -1, 1, -1, 1, -1, 1. It goes up, down, up, down, up, down. A limit means it's getting very, very close to just one value. It's kind of shrinking in towards just one value. And this thing does not shrink in towards just one value. It shrinks in towards 2 values. It's -1 for a lot of the time. It's +1 for a lot of the time. It's never settling down to just one number. The limit does not exist. And the limit is not infinity or minus infinity. It just doesn't exist. So that is why it is the way it is. The limit does not exist, but is not minus infinity or infinity. And if you wanted an explanation in words, you could say because it jumps between -1 and +1, never settles down. That is one way to write it. Okay, and this is quite different than what we saw last class. At the end of last class, we did this example, the sequence 2, 4, 8, 16, 32. And this one, the limit did not exist. But the limit did not exist for a different reason. The limit did not exist because it was going up to plus infinity. So going up to plus infinity is one way the limit doesn't exist. And jumping around between two different values is another way the limit does not exist. And it's sometimes you need to know the difference, but sometimes you don't. Sometimes you just need to know, does it exist or not? These are two different examples where the limit does not exist. Yeah? Yes, that is true. So last class, we said both of these things happened. But actually, as soon as the limit is at plus infinity, the other one automatically happens. So the limit is plus infinity automatically means does not exist. So I think the way I would think about it in my brain is infinity is a special type of does not exist. There's all sorts of ways the limit might not exist, and infinity is one of those ways. If the limit is infinity, it automatically does not exist. But like we saw on the other thing, sometimes when the limit does not exist, it is not infinity or minus infinity. So it can, if it doesn't exist, it could be infinity or not. If it's infinity, then it automatically does not exist. Okay. In the earlier class, I used an example of a chair, and I said every chair is a furniture. Let me roll out a chair so you guys can see what I'm talking about. Here is a chair. A chair, okay? If you look at this and you say, what is this thing? It would be correct to say it is furniture. It would be even more specific and correct to say it's a chair. In the same way, with that limit over there, if you say the limit is plus infinity, that is specific and correct. If you say it does not exist, it's true, but what kind of does not exist is it? It's a special type of does not exist. It's infinity. So on the exam, when we ask you what is the limit, we're going to ask you to be as specific as possible. If you can figure out if it's infinity or not, you should say so. Okay, so in this analogy, a chair is plus infinity, and our limit is plus infinity, and furniture is the limit does not exist. If it's a chair, it's automatically furniture, but there are pieces of furniture that are not chairs, like tables. Okay, I'm going to stop with the dumb analogy. Any questions or comments about this example or the previous example? Those are two limits that did not exist in two different ways. Yeah, there's a question over here. Yeah. I think the answer is going to be it depends. So if it's alternating between 5 different values, and the 5 different values are all really different, and it just goes between them all, then the limit would not exist in that case. But there are other tricky situations where there's sort of like 5 values, but the 5 values get closer and closer to 0, and then the limit would be 0. So I wouldn't want to make a general statement like, if it's like this, the limit exists or not. I think you really should look at case to case what happens. And there will be one example where I'll tell you like 4 different things to sort of memorize. But in general, you shouldn't like presuppose what happens based on the number of cases. I would look at each one individually. Yeah, it's a very good question. Okay, so what is next in the notes is definition 60. And definition 60 is just a word to go with the ideas that we've been talking about so far. So there's the word converges and the adjective convergent. Adjective, right? This is an adjective convergent. And converges and convergent, they mean the limit exists. So these mean the limit exists. The limit exists. The opposite are the words diverge and divergent. This is the adjective version of diverge. And these mean the limit does not exist. The limit does not exist. Okay? And the second one, diverges and divergent, includes infinity, and it includes the cases where it doesn't exist but is not infinity. All the types of not existing are called divergent. So you could, very nicely say the previous example we just did is this example over here, this is a divergent sequence. That's accurate because it doesn't exist. This is another divergent sequence because the limit does not exist. So it's just a way of a new word that tells you what these things are. OK, yeah, like in the notes it says the last two sequences are divergent while the previous examples are convergent. OK. All right, in the rest of the class, we're going to try to build up to doing harder and harder limits. So there are going to be more and more complicated sequences. We've seen a few already. They were all relatively simple. And we're going to see how do you solve more complicated sequences. And we're going to start with this result. This is the limit of the sequence b to the power n. And I think the way you should think about this is this result, result 31, this is a building block. This is a building block to more complicated sequences. So the way we're going to solve hard limits is we're going to learn a few special limits. Result 31 is one of these special ones. I call these things like the most basic building blocks. And then we're going to combine building blocks to solve harder and harder limits. Another way you can think about this is if you like chemistry, this is like an atom. And we're learning about the special properties of this atom. And then later, we're going to combine many atoms to get a really big, complicated molecule. And by understanding the individual atoms and how they connect, we can build up to very complicated things. So this simple building block, this is the limit of a geometric sequence. The limit of a geometric sequence. Maybe I should say it's a special geometric sequence. A special geometric sequence. So b to the power n, that's what we call the geometric sequence. And this is the common ratio. We're always multiplying by b. And depending on what b is, there are 4 possible things that can happen. The limit could be 0. So the limit could be 0. The limit could be 1. The limit could be plus infinity. Or the limit does not exist. We just did this last example in the case of b equals minus 1. Example, b equals minus 1. We just did that example. That was literally the example we just did. So when b equals minus 1, that falls into the does not exist category. And that looks like this, right? This thing, minus 1 plus 1 minus 1 plus 1, the limit does not exist, but is not infinity or minus infinity. That is the last branch here of the little answer booklet. OK, what about the other ones? Here are some examples. In exercise 138, they do the example 3 to the power n. What does the sequence 3 to the power n look like? Well, when n goes from 1, 2, 3, 4, I'll ask the people in the back to stop talking. Thank you. So when n is 1, 2, 3, 4, 5, what is the sequence 3 to the power n? There's 3 to the power 1, which is 3, right? Anything to the power 1 is 3. 3 squared is 3 times 3 is 9. 3 cubed is 27. 3 to the 4 is 81, and so on, ... So it goes 3, 9, 27, 81. It looks like the numbers are just getting bigger and bigger forever. Let's see what it looks like on Desmos. So let me freeze this one, and I'll put it on Desmos. And so I have this thing set up in Desmos that I can just change the value of b to whatever I want, and it will make the graph. Let me get rid of the lines for now. And let me make b equals 3. b equals 3. OK, what happened? Oh, we have to zoom out. So b equals 3, and we have to zoom out like this to see the values. OK, there we go. There we can see the first 4 values. We can see the first 5 values. So it goes 3, 9, 81, 243. The numbers are making this exponential curve. They're getting bigger and bigger forever. And if you keep zooming out, you'll just see the numbers get bigger and bigger forever. And they get bigger and bigger forever. The limit is what you expect, which is plus infinity. So the limit is plus infinity. And that is exactly this case. B equals 3 is one example of that one. OK. Let's do another example. Let's do the case minus 1/3 to the power n. And again, the notes want us to fill in the first few values. When n is 1, you get minus 1/3 to the power 1, minus 1/3. When n is 2, you multiply by minus 1/3 again. So minus 1/3 squared. And minus 1/3 squared, it's a negative times a negative, which is a positive. And on the bottom, you have 1/9. So the thing to watch out for is it went negative positive. And the next term is going to be negative again. So to get from one term to the next term, we're multiplying by a negative number. We're multiplying by negative 1/3. And so the next term is going to be negative 1 over 27. And the term after that is going to be positive 1 over 81. I think you can see the pattern between example A and example B. They are related. The numbers are the same, but example B goes a negative, positive, negative, positive, negative, positive. And now you might be tempted. We saw an example with negative, positive before, and I said because it was going negative, positive, therefore the limit does not exist. I said that on our warm-up example today. But this one, is it like that? Do you think the limit exists or not? Let's look at Desmos and take a look. Let's take a look in Desmos. All right, so I'm going to zoom in. I want to change b to negative 1/3. Negative 1/3. And I have to zoom in a lot here because I zoomed out a lot before. So let me zoom in a lot this way. Nope, not that way. Okay. Zoom in, zoom in, zoom in. Okay. Zoom in more. Okay, and zoom out a little bit this way. Okay. So what is this sequence doing? I think this one, you see the dots. They go negative, positive, negative, positive. Let me also draw the lines. Let me add in the lines here. Lines. So they go negative, positive, and it is true they're going negative, positive. Every other term is either negative or positive, but they are sort of shrinking in towards 0. This one, to me, it's like a door that has a spring on it, right? It's like you open the door and it goes, and it like overshoots and undershoots and overshoots and undershoots, but it's getting close to the door being closed. So it's just like that over here, negative, positive, but shrinking in towards 0. The limit of this one is 0. It's exactly 0. It's exactly 0. And you could say because it shrinks in towards 0. Okay. That was negative 1/3 to the n. I want to show you something cool. So we had this way of looking at it, right? Where you plot the values as the y values. We had the other way of looking at it as well. And the other way is this way of looking at it, where you have things like this. Let me turn the labels off. So this was what I called, in the notes, this was called method 1, right? Where you plot the values as the x values, and you see the sequence goes negative 0.333, positive 0.111, negative 0.037, positive 0.01. So it's kind of going back and forth, back and forth. This is the method 1 way of looking at it as x values. Why did I want to show you this? The reason is because I realized I bought a new mouse. And this new mouse, it has this really nice trackball where if you just spin the trackball, it will keep spinning. Why is this cool? The reason it's cool is because if you do it, it looks like this. Whoa. Okay, and then I realized I said something last class, which was that it's really good with the Hypnotoad music. So I got that ready. So here's the Hypnotoad. And here's us zooming in on the function. And that is why the limit is 0, because you just zoom in forever, and you just get closer and closer to 0. Look, we're at 10 to the minus 15, and we're zooming in. That's what we did in math class today. Okay, I'm going to stop. So the limit is 0, and now none of you will ever forget. Okay. Okay, so the limit is 0 because it shrinks towards 0. You saw it in action. It was going left, right, left, right, left, right, but they get closer and closer to 0. That's why the limit is 0. Okay. Any questions or comments about A or B or this result so far? So far we've covered this case. That was example B. Example B was like this. Example A was this one, where the limit was example A. Okay, and we did this one. That was an example we did before. We're about to do example C. Example C is similar to something else, but any questions or comments about that? Okay, let's do this example quickly. Example C, this is very similar to the case b equals minus 1. It's minus 2 to the power n, so here b is minus 2. So it's the powers of 2, but they have a negative sign in front of some of them. So when n equals 1, you get negative 2. Negative 2 to the power 1 is negative 2. When n equals 2, you have negative 2 squared. A negative times a negative is a positive. You have positive 4. Positive 4. What about the next number? Well, you multiply it by negative 2, you get negative 8. Right? So it's going negative, positive again. And this time it's giving you big powers of 2. So what is the limit? What is the limit? Let's look at it. Okay, and we got to zoom way out, because right now we're zoomed in at 10 to the minus 19. We need a new sequence. The new sequence is the sequence with b is negative 2 b is negative 2. Okay, where's the negative 2? Okay. I'm at 10 to the minus 9. We got to zoom all the way out to see it. There we go. Okay. So there are the numbers. I suppose it's easier to look at the other way. Let me go to the other way of looking at it. And let me turn off the lines. Okay, and let me zoom out some more. So here's the sequence. And let me try doing this. Okay. Oh boy. One moment while I try to sort this out. Okay. So here's the sequence. It's hard to graph these exponential sequences. Okay. We're getting close. Okay, here we go. This is a good illustration of what is the sequence doing. So the sequence goes negative 2, 4, negative 8, 16. So it's going up, down, up, down. And the amounts of up, down, they get bigger and bigger. So now that you can see it, you can draw with the lines what's happening. Let me draw with the lines what's happening. Let me turn this one on and turn the lines on. Nope, not that one. This one. The lines. Okay. So it's going up, down, up, down, up, down. Does it ever settle down to just one value? No. So the limit does not exist. Is the limit infinity or minus infinity? This is a more subtle question because it does look like the values get very, very large, but they get very, very large in positive and very, very large in negative. They never actually settle down towards minus infinity or plus infinity. So in this example, the numbers are getting really big, but they get big in positive and big in negative, and that is why the limit does not exist. So the limit does not exist. And to be super specific, but not infinity or minus infinity, right? It's neither infinity or minus infinity. That would be if it just got big forever or it just went down forever. This way it's alternating, and so it doesn't exist, but it's neither infinity or minus infinity. And that is exactly the same case over here. This is the example C is when b is minus 2 is like this. Okay, I hear lots of people talking. Are there some questions? Yeah. Yeah, so in this situation, the example A was this case, where b was equal to 3 and the limit was plus infinity. And plus infinity is a type of does not exist. So if you want it to be really specific, you could say does not exist and is infinity. Like that would be even more specific. If you write plus infinity, we all know that plus infinity is a special type of does not exist. So you don't need to write down does not exist. We know when you write down plus infinity, you're automatically saying it doesn't exist. Yeah, no, that's a good question, and I think this is like a subtle thing about infinity and plus and does not exist that people don't talk about enough. Okay, I'm going to add into your notes. I said we have this building block of the sequences Bn. I'm going to add in one more building block, and I'm going to add it in. Where should we add it? Let's do it over here. I'm going to right above. I'm going to do the limit of the sequence. I'm going to do the limit of the sequence n to the power a. What is the limit of the sequence n to the power a? So in your notes, it says the limit of these geometric sequences, b squared, b cubed, and so on. We did that. I'm going to do this new sequence, which is 1 to the power something, 2 to the power something, and so on. This limit is very easy. The limit as n goes to infinity of n to the power a is always plus infinity as long as a is bigger than 0. So the limit of n to any power is always plus infinity. If you do n, 1, 2, 3, and you square them or cube them, it doesn't matter what power you take them to, the limit is plus infinity. This building block we are going to use later on, so I thought we would include it now. I'm going to do one other building block, and I'm going to try to squeeze it in right in the corner over here, which is the limit of n with a 1 over n to the power a. So what if you do 1 over n to the power a? Well, if n to the power a is getting bigger and bigger and bigger, then what is 1 divided by n to the power a doing? You're taking a really big number and you're doing 1 divided by a huge number. That is getting close to 0. So the limit as n goes to infinity of 1 over n to the power a, this is equal to 0. So these are two building blocks that are not in your notes, but we're going to use later on. And so I think they're worth including. Now we have 3 building blocks. We have geometric sequences, and we have these n to some power and 1 over n to some power. Those are 3 different limits that we can combine, and we can combine them to get more complicated limits. Okay, and this is, again, you need a bigger than 0. Need a bigger than 0. Okay, so what are we going to do? We're going to start with this problem, which is a lot later in the notes. It's on page 316. It's exercise 140 on page 316. It's the limit of 1 minus 0.2 to the power n. And this is the kind of limit that we want to be able to do. This limit is not on our list of building blocks. So just like a complicated molecule, like the molecule for water, is not an atom, we don't understand what it's doing, but we understand the individual parts. And that's because it has two simple parts. It has this part, the 1, and it has 0.2 to the power n. And I can understand either part individually and then combine them. So here is my solution. I'm going to think of the sequence 1 minus 0.2 to the power n as made of two parts. Two parts. There's the sequence an, which is always 1. That's the first part in green. The sequence 1, 1, 1, 1, 1. That's a sequence. And I know the limit of 1, 1, 1, 1, 1. The limit as n goes to infinity of an, what is the limit of 1, 1, 1, 1, 1, 1, 1? It's just 1. If you're 1 forever, the limit is 1. So that one is really easy. It's like a sort of a baby limit. What is the limit of the sequence that's always 1? It's 1. The other sequence is this 0.2 to the power n. 0.2 to the power n. So what is the limit as n goes to infinity of this sequence? That's the limit as n goes to infinity of 0.2 to the power n. That, in principle, is a hard limit. Like, how would you do that limit? That would be a lot of work. But fortunately, we just did it. We just did it. That was exactly the case when b equals, this is geometric, with b equals 0.2. So on that last result 31 that we just finished, that is exactly the limit of 0.2 to the power n is exactly the case when b is 0.2. And what is that limit? This is one of the cases where the limit is 0. By the way, if you don't believe me, you can check as well, right? So you can check this way. You can put in b is 0.2 and see what happens. I guess we can do it the other way this time. Let's do it this way. This is one of those ones where you can zoom in forever and you can get the nice hypnotoad effect, but it's all on one side. So the sequence we saw before was alternating. This one is going to 0 only from the positive numbers. So it's getting closer and closer to 0 forever. So the limit is 0, but it's always positive. Very similar to one we saw before. In any case, the answer is the limit is 0. So the limit of one piece was 1, the limit of the other piece was 0, and now I combine. So I combine, and I say, therefore, the limit as n goes to infinity of 1 minus 0.2 to the power n. So we have these two things, we're subtracting them, and there is a rule that says you can subtract the limits, is equal to 1 minus 0. And if you want to be very technical, you could say by the minus rule for limits. By the minus rule for limits. Which is, so 1 minus 0 is of course just 1. So the final answer is 1. The limit equals 1. Where is the minus rule for limits? You've probably never seen it before. It's on the previous page. On the previous page. So here are all the different rules you can use. I just showed you why you might care about these rules. If you don't have an example and you don't see why anyone would care about these rules, it seems a little abstract. But these are the rules for limits. And they say that if you know the limit of one sequence an, you know the limit for an, and if you know the limit for the other sequence bn, then you can combine them to get the limit of various combinations of a and b. So there's part I is the plus and minus rule. Plus and minus rule. That says you can add and subtract the limits. We just used that one. We did the limit of the first bit, we did the limit of the second bit, we subtracted them to get the limit of the combination. It also works for products. I'll call this the times rule. Times rule. The limit of a constant is a constant. We did that one too. We said the limit of 1, 1, 1, 1, 1 is just 1. Limit of a constant. This is the next one is the constant multiple rule. It says if you multiply your sequence by some constant, then that multiplies the final limit. The constant multiple rule. Next up is the divided rule, division rule. And there's one extra thing you have to watch out for in the division rule is that when you divide, the thing you better divide by better not be 0. So no dividing by 0. That is important. Okay. And last but not least, I call this maybe the power rule, constant power rule. Let's just call it the power rule. Power rule. So if you have some power and you do the limit of something to the power p, you can do the limit to the power p. So there's an example like this as well. And all of these rules tell you that if you know how to do the limits of the individual pieces, you can combine them to get more complicated limits. So we just saw an example just like that over here. This one was using the sum rule. And in general, you can combine these in all sorts of complicated ways, along with the building blocks that we have, to do basically any limit. And the limits can get extremely complicated, because as you can, just the same way you can make really complicated stuff out of simple Lego bricks, you can combine them in all sorts of ways. So the problems can get quite complicated. I'm going to have you guys try exercise 141 on your own first, and then we'll go over the solution. But this is a good place to stop if there's a question or a comment about stuff. Okay, so why don't you guys try exercise 141, see if you can use the rules to find this limit. And I'll open it up on Math1030 in a second. What do you think? I'm going to open it up on Math1030, so you'll have a choice. Okay, so I just opened it up on Math1030. You can put in your answer now. Okay, there's like 20 seconds left. It's okay if you get it wrong. It's multiple choice, so just take your best guess. I want to see what people are thinking. We will get the right answer, but for now, I just want a rough guide. Okay. Okay, let's take a look at the answers. What do people say? 0 and 1, not too popular. 0 divided by 0, not very popular at all. Of course, 0 divided by 0 is not a number at all. This is some sort of nonsense mishmash of symbols that doesn't mean anything. Infinity, quite popular, but also infinity divided by infinity, also quite popular. The correct answer is, of course, something else. All of these are wrong. All of these are wrong. Only 13% of people are on the right track here, that it is something else. Let me talk about these wrong answers, infinity and infinity divided by infinity, and how you probably got them. Okay, thanks. So this question, it's very tempting. I did this whole shtick about dividing up things into pieces. It's so tempting to just look at this and say, that's a piece, and that's a piece, right? We have two pieces, the top, 2n plus 3, and the bottom, n plus 1. We are going to do the limit of the two pieces and then divide them. It's so obvious. It looks just like the problem before. How could it not be this? Of course, it isn't going to be this. And the reason is that if you actually go to do the limit, what is the limit as n goes to infinity of the top? 2n plus 3. This is the top only. Top only. That's something. And what is the limit of the bottom? The limit of the bottom only is n plus 1. This is the bottom only. bottom only. These are both limits. These are both arithmetic sequences. The sequence 2n plus 3 is the sequence when n equals 1, it's 5, and then it goes up by 2. So it's the sequence 5, 7, 9, 12, 14, and it goes up by 2s forever. And the limit is infinity. The limit is infinity. If you weren't sure that the limit is infinity, you could do that limit using the building block of what is the limit of the sequence n to the power 1. So however you do it, the limit is going to be infinity. And the same kind of logic holds for the bottom. So the top only on its own goes to infinity. The bottom on its own is the sequence 2, 3, 4, 5, 6. Where does 2, 3, 4, 5, 6 going on forever go? It also goes to infinity. So if you do the top and the bottom on their own, they are both infinity. You would write the limits are infinity. And then it would be very tempting to write, it would be wrong, but tempting, so don't do it. It is wrong. It is wrong to say, let me get rid of this little m here. We want the m to go away. Bye. Okay. It would be tempting to say that this is infinity divided by infinity. Don't do this. This is wrong. So in the same way 0 divided by 0 is a nonsense number that makes no sense, infinity divided by infinity is a nonsense symbol that makes no sense. Remember, when we say the limit equals infinity, when we say equals infinity, that is not a number, right? We're not saying the limit is a number and the number is infinity. We're saying the limit doesn't exist and the limit goes up to a really big, it goes on forever. Like this is not an equal sign between numbers, it's more of an is. Infinity is not a number, you cannot divide it, you cannot include it in arithmetic operations like this. It just is not infinity divided by infinity. The other reason to know it's not infinity divided by infinity is technically, to get to this, you would apply, just like I did over here, you would combine, and you would combine by the division rule. The division rule, right? So the rule that technically says if the limit of the top is something and the limit of the bottom is something else, then you can divide the two answers. That is the division rule, which was on the previous page. This rule, right? Rule 5, the division rule. It says that the limit of something divided by something else is the limit of the tops divided by the limit of the bottoms. These rules, and every single one of these rules over here, these rules only apply, and this is so important, we should highlight it, they only apply to convergent sequences. I don't know, how do we emphasize this? In the last class, I drew a little man jumping up and down to remind you that this is important. So he's saying, watch out. Watch out. Here's my man jumping up and down. His hair is going crazy. I don't know. All of these rules only apply to convergent sequences. Convergent sequences are sequences where the limit exists. If the limit does not exist, then none of the rules apply. So if an or bn are divergent, then there are no rules. Then no rules apply. I won't say there are no rules. I'll say no rules apply. No rules apply. Okay. And that's exactly what's going on here. If we look at our specific problem, if you try to divide this up by doing 2n plus 3 divided by n plus 1, none of the rules will apply. You will not be able to find the limit by doing the limit of 2n plus 3 and doing the limit of n plus 1. There is no rule that tells you what happens in that case. Okay, so what's the conclusion? You might think the conclusion is, we're screwed. We just can't do this problem. That's not the conclusion. The conclusion is, you need to be a little more careful about how you divided it up. So dividing it up by just top and bottom is not the way to go. What you got to do is before you divide it up, do a little algebra to make the top and the bottom nicer. So the actual solution, all of this is sort of going nowhere. The actual solution is going to be to first divide the top and the bottom by n. And if you do that, the 2n plus 3 divided by n plus 1 is equal to 2n plus 3 divided by n plus 1 divided by n. So if you do something to the top and bottom of a fraction, it doesn't change the fraction. Those two things are definitely still equal. And now I can simplify. 2n divided by n is 2, and 3 divided by n is 3 divided by n. And n plus 1 divided by n is 1 plus 1 over n. Okay? So I've taken the thing and I've massaged it a little bit. I've done algebra on it to simplify it. And now I'm ready to divide it into two pieces. Now it will work to divide it into a top and the bottom, because the top and the bottom will be convergent sequences. Before they were divergent, but now after working on it, they are convergent. Now I will be able to use my rules. So what are the two limits? The limit of the top, the limit of the top is the limit of 2 plus 3 divided by n. What's the limit of 2 plus 3 divided by n? By the sum rule, if you want to be very fancy, you could say by the sum rule for limits, it's the limit of 2, 2, 2, 2, 2, plus the limit of just 3 over n. So it's going to be the limit of the first guy plus the limit of the second guy. What's the limit of just 2's? That's 2. We've done that one before. The limit of just 2's is 2. What is the limit of 3 divided by n? The limit of 3 divided by n, it's 3 divided by a big number. Imagine n is getting really, really big. 3 divided by 1,000, 3 divided by 1,000,000, 3 divided by 1,000,000,000, it's getting closer and closer to 0. The limit of 3 divided by n is 0. And you could just logic it out like I just did, or you could use the building block that I said, that the limit of 1 over n to any power is always 0. That was one of the building blocks that we had. So the limit of the top is 2 plus 0. What is the limit of the bottom? Actually, before I do the limit of the bottom, any questions or comments at this point? Let's do the limit of the bottom then. The limit of the bottom is the limit of 1 plus 1 over n, and just the same way we did the limit of 2 plus 3 over n, the limit of this one is 1 plus 0. So the limit of the sequence that's always 1's is 1, and the limit of the sequence 1 divided by n is 0. 1 divided by a really big number. As the number gets bigger and bigger, 1 divided by the number gets closer to 0. That was also one of our building blocks. Okay, we've done the limit of the top. It was 2. We've done the limit of the bottom. It was 1. There is one last step, which is to combine. So maybe we'll combine all the way over here. We'll combine. And the division rule says, if the limit of the top is 2 and the limit of the bottom is 1, what is the limit of the whole thing? The limit of the whole thing is the ratio 2 divided by 1. 2n plus 3 divided by n plus 1 is equal to 2 divided by 1, which is 2. So the final answer is 2. That is the final answer. How did we get 2? First, we had to do this massaging. We had to do some algebra to simplify it. And we simplified it into a way where we could see it into two parts, where the top part was 2 and the bottom part was 1. And then the division rule says you can divide them to get the final answer. I will tell you, there are lots of these problems to do. Here are 2 more of them. These are going to be extra videos. And you have lots of homework problems with them as well. We're going to be doing more limits next week. We're going to be doing limits of functions instead of limits of sequences, but it's definitely worth your time to practice doing these limits. Practice this idea of cutting things up into blocks and doing algebra simplifications. I'll answer your question after. Yeah. Okay, we'll stop there. See you guys on Friday. And if you want to come ask me a question, I'll be here for a while.